Oh, yeah.
Hello. Okay. So we're going to do the second lecture.
Oh, yeah, sorry, I've been drinking.
So we're going to do the second lecture on the reasoning and the planning abilities of large language models. If you remember yesterday, we did this first part, the perspective on LLMs and their approximate retrieval, understanding, reasoning, and planning abilities of standard LLMs, and ideas for improving. That's what is used in the reasoning models. LLMs as generators, test time scaling, and as the LLM-Modulo and post-training. I sort of gave a quick overview of that, and in today's lecture, we'll drill down on the planning abilities of standard LLMs, especially right out of the box, or with chain of thought, with ReAct, with self-verification, all these things, and half of this is to point out that they actually have limitations, and all of this stuff is referred and published and so on. We'll talk about that. Understanding what the limitations are about those sorts of things for large language models is what we do. And then in the second part of today's, this particular lecture, we will shift into test time scaling and large LLM-Modulo. And then this afternoon, we'll continue with post-training methods. Okay? So that's the deal. So yesterday I kind of suggested that you might do some beach reading. Maybe you did some of that. Those are the links on the Twitter. And then I also recorded the lecture audio. It's being recorded again right now too. So I posted that too in case you want to review the again. Okay. And then this is the lecture two. In case you want the lecture slides, if you want to take a picture of that, that's basically the lecture slides. And I also tweeted the link if you want to follow along. Okay. Before I go forward, are there any kind of questions from the first lecture that anybody is going to ask? I know some of you already talked to me, after the lecture and so on. And again, as I said, in the coffee break today, as well as the rest of the day, you can ask me more questions. But so that's the lecture slides in case you take everything. Okay. So I'm going to go into the lecture two. So basically, as I said, we're going to look at planning, reasoning abilities. So the word reasoning is sort of questionable definitions, lots and lots of different definitions. So planning is a particular form of reasoning. It is reasoning over time and change, and in particular, the specific, like concrete examples that I'll be looking at as benchmarks would be things like blocks world, where you have blocks in one configuration, you're going to put them into a different configuration. You have logistics, you have a bunch of things in different warehouses, you need to shift them from place to place to actually reach a separate version. And then we will see as we go along that we not only look at normal definitions of these domains, but also sometimes change the names partly to see whether LLMs are actually reasoning or are they remembering. This is one of the big issues, when you actually train these models on the entire universe of data that we have available. It's hard to tell whether they're reasoning or retrieving. Okay. All these models actually in the community that I come from, automated planning community, they basically, there's like a formal way of like a language for representing these, but basically, if you hate parentheses and lists, then it's really not that hard to see that all they're talking about is actions have preconditions and they have effects. And basically there are different actions. So in this particular case, you have, in the domain blocks world, you can pick up, you can put down, you can stack, and you can unstack. And a problem is specified by the initial and goal state, and then you're supposed to provide, you're asking the LLM or the planner to provide a sequence of actions that when carried out will reach the goal state. Okay, you can produce. We actually can in the case of GPT-4 we can either prompt it this way, or we can actually prompt it in more like natural language fashion. So both have been tried. So essentially this way, the same thing. If you hate parentheses, actually some of us love parentheses. We are lispy folks, but if you hate parentheses, this is sort of pseudo English version of the same thing. Okay. The other thing, of course, is if you are thinking in terms of these sorts of representations, actions with preconditions and effects, this is some of the simplest version of these things are what's called strips planning domains, where essentially you have preconditions and effects, and what sort of problems can you represent. One of the problems that you can represent in this turns out to be tower of Hanoi, which is kind of a strange thing to talk of it as a planning problem, but it can be represented in this. And this is part of the one of the examples that Apple paper actually used. And so you are suddenly seeing on the news, towers of Hanoi moving about. One interesting thing about Tower of Hanoi, it turns out, is it actually tells you approximately that the computational complexity, worst case computational complexity of solving a planning problem represented in this language is not NP hard, but it's actually p-space complete. Because in the case of Tower of Hanoi, the answer to the problem itself can be exponentially long in the input size. I don't know if you heard about the whole stories about Tower of Hanoi and the legends and so on, that there are these towers of Brahma or towers of Hanoi, where essentially these priests are slowly pushing these disks from this place to this place, and they should never have a larger size disk above a smaller size disk and at any point, because otherwise the world will come to an end. And then the world will anyway come to an end when they have successfully transferred everything. And it turns out there are, apparently they're trying about 64 disks. So you should not be too worried, because 2 power 64 would be the length of the solution. And priests are not exactly activity kind of people, they're moving very slowly, so the world will be around for a while. Okay, so that's Tower of Hanoi. The other thing I mentioned, which also can be represented in this kind of a language, just to give you a sense of the kinds of problems here, would be Sokoban, which is a very simple domain where you get to only push the boxes. This guy gets to push the boxes into a particular, they start from a place and you need to put them into a particular configuration. This is actually, unlike blocks world, where actually pretty much from any state you can reach any other state, even during execution. Sokoban is a truly non-ergodic domain, because if you push the box into a corner and it's not the right place for it, you can't pull it out. So you're dead. So you have to think. The whole point of planning is you think before you act. That was the important thing. Okay? So keep that in mind. We will give you some examples of Sokoban too, but actually even blocks world, LLMs were doing pretty badly. Okay, so we tried, basically we set up like a flow, this was back in 2022. This is ancient to some extent when we started this, where essentially you basically take these problem files and then you can give variety of different ways of prompting the underlying LLM, either with PDL or with language, or single zero-shot, multi-shot prompting, everything that you can think of has been tried. And then we'll also talk about chains of thought and all that stuff later. So this is like one of the older papers. This is actually foundation models for decision making, Tulips 2022. The story there was, it was like a huge large workshop. God knows, 1,000 people or so in New Orleans, and pretty much everybody was saying they can dice and slides, and all sorts of planning can be done. And then this Karthik, the first author here, was standing there with his little poster saying, no, they can't, a bunch of these kind of cases. So that's where it started. Essentially, basically, even for blocks world, if you just go directly ask LLMs, what is the sequence that will correct, which will actually solve this problem. And remember, one of the things for this is because of the models, you can verify the solutions. It's not a question of people guessing, whether or not the solution is correct. It's like there are formal ways of verifying the solution. So, and it turns out the generation accuracies are really, really bad. And this was 2022. And so there's actually a little paper there that, that was the first one that we written. And one of the interesting questions was because people haven't seen things like even block word stacking. Sometimes in the LLM literature, people started questioning, maybe people can't do block word stacking either. I mean, these are kids who probably never played with blocks. It turns out we actually asked people, we paid money to people to see whether they can do block word stacking. They get bored to death, but yes, they do it pretty reasonably, like 78% accuracy and so on for, block word. Okay, so then there is a NeurIPS longer paper which actually gives all the details about how we set up the experiments and how the various different types of prompting strategies and so on. And then there is a second NeurIPS paper in 2023 which also provides a benchmark, plan bench, which is actually these sorts of planning benchmarks. And in some sense, the Apple was essentially doing those sorts of sort of the benchmark from plan bench. Okay. And then we were looking at multiple things. Mostly I will be talking about plan generation, but there are other types of planning related problems that you can look at to see if LLMs are good at it. And as I said, plan generation, task optimal planning, verification, reasoning about execution, bunch of different sub-problems are available on that benchmark. And the long story short, which as I said sort of yesterday, the result of all these experiments is that LLMs actually cannot do planning in autonomous mode. Standard LLMs. Remember, we will get to the reasoning models this afternoon afterwards when we start. Standard LLMs, despite the fact that people thought they could do planning, they can't. And it should not be surprising. And if you heard what I was telling you yesterday, that there's no real reason to believe that GPT-4 sort of models will just automatically do planning. They may be able to remember plans, but they don't necessarily know how to. They may not actually reason. Now, one of the issues. So that's basically the stuff I already showed you yesterday, that we actually continued checking. This was actually on units 2023, but these results are from 2024 with the CoT 3.5, GPT-4o, Llama, and Gemini Pro models, and they all basically not only, they seem kind of improving in the box world instances, and one of the interesting questions with LLMs that you always have to consider is the possibility that there is a contamination. That means more and more of the benchmarks that you have will become part of the web, and the web becomes part of the next generation training. And so the question basically is, are they remembering, or are they actually solving, figured out how to solve lots of problems? And one of the things, as I said, mentioned yesterday, and I'll go into detail now, is we actually obfuscated Oxford domain words, so that if you just remembered and you were regurgitating this answer, you won't do well. And the way, so basically, if you want to check whether something with huge amounts of memory is reasoning or regurgitating, it's actually a pretty tricky issue. And so you have to come up with these kinds of diagonalization arguments. So we did this. If you have something like Oxford here, picking up a block, we call it attacking an object. Unstack a block from the top of another block, feast an object from another object. So basically change the words. And this one is actually kind of words that have very different meanings potentially for people. We also have random strings. There are versions of this where you just use random strings instead of predicates. And it turns out this and this are equal as far as any planner is concerned. Because if you forget about, if you think in terms of logical terms, the meaning of a predicate comes from how it is connected to other predicates. And so the dynamically is the exact same system, and so a planner that can solve this exactly in the same amount of time. But obviously, what we found was LLMs die, essentially. So to some extent, what is happening is maybe the box word performance that seems to be improving probably is improving more because of retrieval rather than reasoning. Okay, this should not be surprising. Around the same time, Tom McCoy and folks, at Princeton actually were talking about this nice example that some of you may have heard of. That remember the GPT-4 was sparking intelligence everywhere. Remember just a while back. And so one of the sparks, after the sparks of intelligence, these guys looked at GPT-4, and one of the things that Sebastian Bubert's paper talks about is GPT-4 out of the box was able to do decoding of Caesar cipher. Encoded things, right? And they wanted to check whether in fact the decoding normally if you understand decoding is basically you take the letter, add an offset, and so that it becomes a different letter, and you change all the letters. And the most standard coding is ROT13. If you know Linux, you have a ROT13 command. And in fact, when you were not born and I was in grad school, one way people will actually exchange files is by doing ROT13 in coding and then doing encoding. Anyway, so they actually check to see how LLM does, not just for the 13 shift, where it does very well, but also other shifts. That is shift 2, shift 3, shift 4, etc. And they found basically that LLMs do very well at 13, but pretty badly everywhere else. Once again, a potential suggestion that what actually was happening in standard LLMs is a memory effect rather than a reasoning effect. If you understand, offsets, even kids can do offset-based decoding, but LLMs apparently couldn't. Okay. One other thing that's interesting, that's mind-bending, is basically why are LLMs so bad with this mystery domain? Maybe if I tell them what I did to the blocks world and say, when I meant feast, when I said feast, I actually meant stack. If I give the actual mapping myself, will they do any better? We give that and they do very better. And more interestingly, if you ask LLM, here is a decoded, here is a mystery domain, what does this remind you most of in the normal sorts of PDL domains? It's a blocks world. So LLMs don't necessarily know. There's usually this thing saying that the man doesn't, your right hand doesn't know what your left hand is doing. In the case of LLMs, they don't even know that necessarily have two hands in this particular case because they can do each of the pieces separately, but they're not putting them together. That's something to keep in mind. Anyway, apparently you're playing too much with this blocks world stuff that once I was looking on Google and for the blocks world, if I give my name, essentially, apparently, I get blocks world as one of the answers. So I've become blocks world myself for some reason. Anyway, so LLMs can't do planning in autonomous mode. That's the Unit 23 results. But then all of you have heard of chain of thought and ReAct, and do they make any difference? Again, for the standard LLMs. Again, these are well-written, well-cited papers. Chain of thought has gazillion citations. Basically, everybody says it works and so on. So the question is it working? And so here is a paper, and you have to give me credit for getting this paper through UNIP's reviewing process. Chain of thoughtlessness is the title. Given that every possible reviewer loves chain of thought, you have to do extra work to convince them. Anyway, so what we basically showed was chain of thought doesn't help in planning problems, either sequential listening problems. And in particular, what happens is when you give, so first of all, what is chain of thought? The basic idea is you give an example and how you solve that particular example as part of the prompt, and then supposedly LLM understands the procedure and does better. That's the basic idea. And it turns out that, so we actually gave it a lot of benefit of doubt. We basically looked at different levels of solving planning problems examples. The most general way of solving any possible planning problem. Next, only just the blocks world problems. Next, only specific subset of blocks world problems that are basically everything is already in the table and you just have to do it one single stack. And next, even more specific subclass, which is you're always having a stack in alphabetical order. And we gave chains of thought examples for each of these. And basically what we find, first of all, is all of them in the beginning, after the example, for the particular problem example that you gave, let's say you gave a blocks world example with 2 blocks or 3 blocks. For 2 or 3 blocks, it does well. As you increase the number of blocks, it dies. And furthermore, the improvement is higher if it is very, very specific type of classes rather than a general procedure. It should not be surprising because this guy is John McCarthy, who happened to have given the name artificial intelligence to the area artificial intelligence. And McCarthy basically said the goal of AI is advice taker program. That basically it should be able to take any advice and be able to follow that advice. And one way of doing advice taking is I give you an algorithm. You should be able to actually execute that algorithm. It turns out LLMs do not have that ability to do that. Once again, in the case of our paper, they kind of redo this point that essentially say that even if you give the algorithm LLMs don't do necessarily well. And that should not be surprising because they don't actually follow advice. And following advice is non-trivial, essentially. Okay, so I can resist saying this, that in general chain of thought basically can be thought of as this capitalist idea that, teach a man, give a man fish and you feed the man for a day, and teach a man how to fish, you feed him for an entire life. But for the LLM man, give an LLM fish, feed it for a day, teach it how to fish 2 fish, feed it for 2 days, teach it how to fish 3 fish, feed it for 3 days, and so on and so forth. So it kind of gets on and on after a while. Again, this is Dale Schulman, who is one of the original authors of CoT, Chain of Thought paper, with Denny Zhu and other people, Jason Lee. And Dale Schulman is giving a talk in ICAPS 2 years back, and he essentially admitted that the same thing is true for chains of thought, that chain of thought kind of counting for reasoning problems. Okay, ReAct is this other thing which is kind of derivative of chain of thought idea, which also got a large amount of sort of interest from the community, tons and tons of citations. And so the question is, again, one of the ideas there is, you not only give an example, you also kind of put these think tags, saying at this point think, and at this point do, and so on. And after you give an example that you're supposed to follow, and basically, in the interest of time, I would say that essentially it also doesn't work for planning. In fact, this particular paper just came out finally in TFLR, and that's just types do think tags really help LLMs plan a critical evaluation of ReAct style planning, and it essentially says that the only times ReAct works is if your example and the problem you are testing on are almost identical. That's the high degree of similarity. So this issue of out-of-distribution generalization, that's a big thing. Basically, it just doesn't happen with ReAct or chain of thought. And in terms of chain of thought, one more thing I want to point out is if this one, last letter concatenation is not even a really particularly hard planning problem. As I said, it's just given a words, take the last letter of each of the words and string them together so that you get a new string. And that's not really a particularly hard planning problem. It's just following a simple algorithm. And even for the last letter concatenation, and this also, by the way, happens to be like the main one of the main examples in the original CoT paper. But what they wind up giving is they give an example and check if it improved for the size of problems for which they gave the example. What we did is we increased the number of words, and if you increase the number of words, the advice is not followed. So it basically gives up. And unlike that, when I tell you this, you should be able to do last letter concatenation. Even if there are 100 words, it may be boring, but it's just basically taking the last letter of each of them and concatenate, but LLMs not. Okay, that's about that tag. And then what if we fine-tune? One of the other things is we do a lot of fine-tuning. Typically, one background issue in much of this talk is how much out-of-distribution generalization are you getting? You can always improve generalization over a small distribution if you basically take that distribution, take like 90% of it, feed it for the training, and test on the 10% left over. But the question is, if you wind up getting larger and larger instances that are in essence similar from a human perspective, that larger number of blocks don't change the blocks world instances, but you did not train the system on more than 3 or 4 blocks world instances, is it actually able to generalize? That just doesn't happen with fine-tuning in general. For the same reason, it doesn't happen with chain of thought and ReAct. And one thing that you want to keep in mind in general is fine-tuning helps if in fact you're sticking to the distribution, almost in distribution, without actually increasing the length. And so it's a strange thing if you realize what you're doing, that this is like you're getting the domain model, you're getting a combinatorial search planner, you make trillion examples of block solved problems, you're making the planner solve them all, then fine-tune GPT-4, and at that point see if it in fact does well on the size of problems that you have tested on. And if you look at it that way, it looks like a Rube Goldberg approach to AI in terms of efficiency. You spend so much time just to actually say that it's able to solve this problem. The whole point of doing fine-tuning should be that it understands the algorithm and goes beyond, and that doesn't happen. Okay, in general, again, the universal order distribution is how machine learning people think about, but if you're thinking in terms of reasoning problems, in terms of planning problems, the out of distribution really is about deductive closure. Okay, and the deductive closure, so basically, if I give you how to solve one block world instance, you should be able to understand how to solve any larger instances irrespective of the length. And if I tell you how to solve one last data concatenation instance, you should be able to solve it even if there are 100 words. And that's basically within the deductive closure. By the way, deductive closure is a pretty well-known idea from logic. If you have background in logic, and you can look it up. If you don't, but that's the part that you want. And reasoning essentially is able to see if something falls in the deductive closure of the base axiom that you've been given, and LLMs don't necessarily do that well. Okay, so on the other hand, the literature seems rife even at that time with LLMs doing planning. Standard LLMs are doing planning. There are lots and lots of papers. These are all prior to ours. And so the question is, what exactly are they missing? And it turns out that it's not that anybody is cheating anything. It's just you basically are missing what kinds of issues make planning problems hard. In particular, planning problems involve planning knowledge. What are the possible actions? What are the precondition effects? What are the general recipes? What are the old examples of plans? This is the stuff LLMs are great at, because pretty much everything that you ever have put on the web may actually be available for training. But they also have planning also involves plan generation and verification techniques, which is making sure that there are no interactions between the different actions, so that what one action achieves, another action is not violating it. In blocks world, that's the kind of thing that you do and get into trouble. Plan merging techniques, plan modification techniques. This is a combinatorial research issue. This is a knowledge issue. Okay, and LLMs do very well on the knowledge part. They do very badly on the search part. That was the basic one. Okay, so they can accept any planning problem even if it's not in the PDL standard, but they don't give any guarantees of what the plan is. And if you check that, then basically you realize that they don't have a good enough performance. Interestingly, in traditional planning, knowledge has always been a bottleneck, because essentially everybody writes a particular domain in the PDL for that particular domain. And one of the nice things about LLMs is you can just say, here is a problem, and they kind of can make sense and provide a reasonable approximate solution, but not necessarily that solution. So it's sort of a complementary thing. So but then when there are interactions between the actions, they become bad. So the easiest kind of planning problems from a search point of view is if you have n sub-goals, and the way of achieving each of the sub-goals can be concatenated in any which order, and the final plan will work. Life would be really, really simple if you have independent sub-goals. That's basically the idea. And so LLMs do actually very well on cases where independent sub-goals exist. And in fact, one of our arguments is most of the other planning domains that people were actually checking on happen not to have interactions. That's why they were doing well. But in general, those are the domains where you don't even need to do planning, because you can pretty much blunder through doing action after action and you won't fail. How do you test this? You can take the blocks word. Remember, it has preconditions and effects. Basically, the normal effects would be that sometimes you add and sometimes you delete a condition. And the deletion is the part that makes actions get into each other's way in the blocks word. And the preconditions are another way where if the action is, you want to do the action, the preconditions are not true by the time you're doing the action, it would fail. Okay? And so one idea is start removing deletes, start removing preconditions. And if you do this, you relax the domain such that it becomes a really, really simplified blocks word domain where nobody gets into anybody's way and any action can be done anytime. And in those cases, LLMs, the green part increases. In those cases, actually, LLMs also do well in blocks. Okay, and the only reason there's still some red left is LLMs don't count well. At least the standard LLMs don't count well. So if there are like n particular sub-goals to be achieved, they might actually miss even putting a plan for one of the sub-goals. That's the only reason they will wind up failing. So these are really, really simplified domains where planning is not needed, and that's where actually LLMs do well. That's basically the point we made. One interesting thing, this is actually a dated example about 1.5 years back. There was like Amazon was full of travel books, and people were essentially, Rick Steves and all these other people will do research and figure out exactly how to come to Italy and have a good time, etc. But they charge $29.95. So Amazon was full of these books at only $19 and have nice, beautiful pictures that are written by diffusion models, etc., etc. And so they look as good. These are all the fake ones. This is a New York Times article. And then people are buying, $10 less, I can go to Italy with this book. And then they're coming all the way to Italy and finding that Uffizi is closed on that particular day. And you want to get into Uffizi, there is this secret number that you have to call and make a reservation, otherwise you will stand these gazillion people lying. These are all the interactions. This is where you actually need travel planning, not to see the pretty pictures, right? And so very soon people are, sending back the books. And this is actually like a macro level of essentially putting together a sort of travel planning book, but that actually doesn't work. It's the logistics that don't work. Another tongue-in-cheek comment is, if you want to get a wedding plan for your wedding, please don't ask LLMs for that. Because all wedding plans look almost the same, and the variations of it can be given to you. Weddings fail not because the high-level plan isn't good, but because the logistics is not good. Somebody forgot to get the ring at the time, or somebody basically, there were no chairs, and who cares about chairs when they're thinking about wedding? Well, you have to care about it, because people don't understand your wedding. So logistics, which is actually the boring part, is the one that winds up making things fail, and that requires reasoning. Okay, so if you want to argue LLMs can plan, then pick a domain with high branching factor of unenumerated action. That means there's so many possible actions and you don't even sit down and write all the ones. Where the interactions are very low. That means pretty much any action can be combined with any action and they don't get into each other's way. And this would be the case when in highly algorithmic domains, and that's where LLMs actually will do pretty fine. Okay? If on the other hand you want to argue that they cannot plan, pick a domain where even they may actually be a few enumerated actions, but there are interactions between them, like the Fox world, and where they cannot actually do the reasoning part. Okay, so knowledge effects, they do much better. Reasoning effects, they don't do well. How many of you have seen the TV series MacGyver? Anybody heard of MacGyver? So MacGyver is actually basically MacGyver planning of certain times LLMs do very well. It's like it looks like there is no action, nothing has been written anywhere in the library. LLMs can suggest you an action. But then checking whether those actions can get into each other's way to see whether the overall plan is correct, they don't necessarily do that. So that was the way. But on the other hand, there is this knowledge effect that is actually LLMs are very good at, as I pointed out. And you can use LLMs to improve knowledge acquisition bottleneck for any AI systems in general, including planning systems. This is like a way of thinking of the old style AI, where you have a bunch of subject matter experts, and then some knowledge engineer goes talks to them, figures out what the domain is, writes them down, gives a bunch of rules, provides them puts them in a knowledge base, and some logical reasoner or something works on them. This is the old style AI that we are supposed to make fun of, right? Because this is a very costly process. Well, to some extent, LLMs provide an approximate way of automating this whole thing. Right, so you can actually just go and ask LLM, I'm thinking of blocks world, what do you think are the kind of actions I might have? What do you think are the kinds of preconditions and effects for those actions? This is what experts are supposed to tell you. LLM can become a super expert because it's been trained on so much data about the world, and then that will give you an approximate model, and somebody can then improve that model. This is sort of like, you let them suggest code and improve. And similarly here, you let them suggest a domain model and improve. And in fact, there's a third paper in ULIPS 2023, we basically show that you can use LLMs to actually tease out domain models. Blocks whole domain model, logistics domain model, etc. With the human in the loop, with the verifiers in the loop, you can improve the model that the LLM gives, so it reduces significantly the amount of knowledge acquisition work that people were doing before. Because this thing knows everything at a certain high level. and so you can actually use that to provide, to get the domain models. Okay, so LLMs actually are now being used to construct world models, even if their current, the world model that might be underlying them may or may not be useful and may not be actually useful in terms of actually getting high enough reasoning accuracy. They can be used to get out domain models of the type that I was giving as part of the prompt in the original prompting, right? So that's a very useful way of using it. In general, with LLMs, the one advantage for planning and also reinforcement learning is for a long time, especially in both planning and reinforcement learning, there was this idea that you should give as little information to the reasoner as possible. Deep reinforcement learning tries to say, just go for pixels. Even if you know something about the domain, if people have to give it, that's a huge amount of work. So let it just deal with the pixels and figure out pretty much easily available knowledge. But if you don't have to give it, if you have an LLM in the loop that you ask it to give the domain, the dynamics, or the reward, etc., that cuts down the knowledge bottleneck and actually improves significantly the efficiency of reasoning. And so, in fact, much of the effect LLMs had on the RL and as well as planning is this knowledge acquisition part. And you basically get that. And then once you have a simulator, once you're actually trying it out in a robotic world, any errors can actually be handled because basically you start with a much more efficient way to solve these problems. Okay, so that is about standard LLMs, and obviously they don't seem to do well, and the kinds of ideas that you heard of, chains of thought, or ReAct, or even fine-tuning are not really helping. So how do we improve? I'll basically walk you through today, right now, in the LLM-Modulo part, which is a test time scaling idea, and then this afternoon I'll talk about post-training and the whole idea of reasoning traces and do they have meaning, etc. Okay, so how do we go from System 1 LLMs, if you remember System 1, System 2, to something which actually does both System 1 and System 2 approximately? That's basically the idea. One of the things, essentially, one of the beautiful things that people fell in love with for LLMs is that at the inference time, irrespective of the cost of the problem, at the inference time, the standard LLMs, the moment you give the prompt and you hit return, it starts blurting out the solution. The solution may be wrong, the solution may be right, but it blurts out the solution in milliseconds flat. Right? That's a good part. So one thing that people started thinking about is maybe it's talking too fast. Let it think a little bit more. Let's pause. So people have tried all sorts of things like put pause tokens into the LLM such that they won't give out solution tokens right away. One of the better ideas in general is essentially basically do extra work during the inference time so that your solution improves. This has been like a big change in the LLM literature, but it's an old idea in AI in general. In fact, originally AI was all online. If you remember Deep Blue, it would do all the reasoning at the time after the opponent makes the move. It then figures out what is the next move it's going to make. And instead, what we did AlphaGo essentially does a bunch of it in the memory part and some part in the online MCP. And you can do even more into the memory part by actually avoiding any of the MCP too. So in general, this idea of doing search time or inference time computation is not new. It was the old idea, but we stopped doing that in the case of LLMs because inference time is very precious. People are extremely impatient, and when they hit return, they want answers, right? And so now we basically say, now they seem to be very unhappy with the accuracy. Can you make them happy by taking extra time? Okay, so that's basically the way of thinking about test time scaling. Some of the simplest ideas for test time scaling is let LLM generate multiple answers for a prompt and basically take the majority. This is self-consistency. It's been called self-consistency. It's all majority voting. The hope is it's trying to remember the answers, potential answers for this particular prompt. And if you make it, guess like 15 times, and if it 10 times out of 15 it wound up giving this answer, and 5 times out of 15 give other answers, then maybe this one is the more important. Usually this thing actually scales well when the answers are multiple choice questions in particular, because there's like a finite number of possibilities, and so you wind up saying, how often is the answer A, how often is the answer B, and if most of the majority of the time A is the answer that's guessed, you assume that it's A, and then you check if it is actually working or not. A more principled way essentially is use LLM as a generator, just as what we did before, but use a verifier in the loop, and that basically checks if the ideas that were being generated are correct or not. And that is essentially the LLM-Modulo idea that basically there's a paper in ICML. So you think of large language model as a generator of suggestions, okay? And you have a bank of critiques. These critiques can be external critiques. They can be learned external algorithm critiques. They can be learned critiques, like you use machine learning to figure out a higher probability of success critique, which tells you whether a plan is correct or not. And they can also be LLMs themselves critiquing. And as we point out, LLMs actually are much better at critiquing style rather than the correctness. I'll actually show you a Linux paper, ICLR paper, that will basically, I started 5 minutes late, so you get me 45. So I'm not LLM. You basically get essentially these critiques, the bank of critiques, and the LLMs are actually good at doing the style critiquing, not the correctness critiquing. The ICLR paper that I'll show you in a minute shows that if you make LLMs be correctness critiques, their performance will worsen because of the false positive and false negative rate. They might have guessed the correct solution, walked all over into a wrong solution and stopped. And that is possible if you are not able to verify. Okay, so in general, you can have multiple critiques in this, and the idea basically is when there is a generation, when a solution is generated, a guess is generated, these critiques basically say yes, no, and also yes, no, this is not correct, and here are the reasons. And so, which becomes a back prompt. Instead of backtracking, it's a back prompting. You basically go back to the LLM, and then it comes up with a new suggestion until this process where the critics are happy. And when the critics are happy, to the extent the critics are sound, you now have soundness guarantees of the solutions that are coming up. Okay, one interesting question is, notice that some of these critiques are actually could be classical. They're coming from plan verifiers, they come from schedule verifiers, etc. They can be classical computer science techniques. But I'm not using them for search, I'm only using them for verification. One advantage of that is verifiers are composable. So you can look at, like if you think of how NASA does its mission planning, a bunch of experts are looking at the mission plan from the point of view of their own constraints and say, okay, I'm fine with it, I'm fine with it, I'm fine with it. And if all the experts are happy, then you hope that this might work. Of course, you may still have things that are unmodeled and you can go wrong, but at least the whole point of it is avoid definite problems that you should have checked for. That's what is happening here. So by using verifiers rather than solvers, if you actually have a verifier, one way of thinking about search is for any problem, if you know how to do verification of the solution, if the solution comes and bites you, you can check whether it's a solution or not, you can always convert it into a search. The simplest way is generate tests. Generate bunches of candidates and see if any of them are correct. And the rest of the other classical search strategies, A-star search, MCP, etc., are doing this process more efficiently so that you don't do repeated work. But the soundness of the overall procedure is given by the verifier in the loop. Okay? So we actually use these as verifiers rather than the solvers. And so we are not using the classical search algorithms at all. We are using either learned verifiers or classical verifiers, or even sometimes LLMs themselves. So as I said, that there can be correctness versus style critiques. Style critiquing actually is very hard. Classical computer science is not good for style. I mentioned it to you yesterday too. LLMs are actually the only game in town that can give you good criticisms about the style. Okay, and whereas the correctness part is basically the plan is going to fail during execution. That stuff you actually wind up using either learned or classical critiques, or classical verifiers. And then there's a whole bunch of extra information about how you can do various ways in which the criticisms from the various critiques are, kind of prioritized, put them together, and you can do different ways of, control flow here, such that you get hierarchical versus parallel versus, sequential ways of doing generative testing. Okay, I mentioned that you should be trying self-critiquing abilities directly, and the reason I say this essentially is the reason people thought LLMs might be better at self-critiquing than at generating plans is because in many classical problems, verification is cheaper than generation of the solution. Okay, that's not surprising enough. But that basically doesn't necessarily mean that LLMs are any better. It's true that it's a lower computational complexity, but lower computational complexity doesn't necessarily mean LLM will do it correctly, because we saw even last letter concatenation, there can be errors in LLM. And so what we pointed out essentially in this paper is if you make LLMs generate suggestions and actually test it themselves, and then you see the overall process effectiveness, it turns out that actually in that case where the LLM is verifying its own solutions, the accuracy can dip before compared to just LLM giving a solution without caring whether it's correct or not. And the reason is there are false negatives. And so you can actually walk over a correct solution, LLM can walk over a correct solution and end up in a wrong solution. Okay? So that's one of the problems with self-verification, and in general that's not recommended if you care about actually guarantees of correctness of the solution. On the other hand, you can do learned criticism, learned critiques, where instead of just the LLM out of the box being used for verification, you can use a version of the same fine-tuning data to discriminatively train the LLM to be better at guessing which solutions are correct. And with respect to the learning theory, it becomes a better critique than the normal, out-of-the-box LLM. And so, in fact, there's a paper, and there are other people too, but this is a paper from our group, which basically shows that version actually does sort of improve performance if you learn the critique as part of that. And as I said, for the solution case, for the style case, this is a CoM paper, this is a conference on language modeling, where we basically showed that if you consider a bunch of behaviors that all achieve the goal, but they might be stylistically not very good, humans might not like it. An example here is you're asking the robot to give a pair of scissors to the human, and the last thing any rational human wants is a hulking winged robot giving a pair of scissors with the pointy end towards the human. And that's a style problem. You have achieved the goal, and if you trust the robot, you should be able to take it. But it's not a good style in terms of giving it in that way. And these are like tons and tons of style issues in general, and they're very hard to model. LLMs are actually a better solution than any classical techniques. So we actually in the CoM wind up showing that you use this to do the criticism of the style of the behaviors, and that can be then used in a bigger system to actually generate behaviors that are not only correct but also stylistically pleasing for the humans in the room. Okay, and we actually also have a paper that shows in HRI that sometimes LLMs can be used to kind of do better sorts of style with respect to mental modeling abilities in terms of whether or not humans are likely to be surprised by the behavior that you're providing. Again, they're brittle. It's not always guaranteed, but it's better than nothing. And then towards the last part I want to mention is, in fact, these are some results showing that both in planning and scheduling kinds of problems, if you use LLM-Modulo techniques of this kind, where with the critiques and the LLM generating multiple solutions, you can improve the performance quite significantly. So this you can think of LLM-Modulo is a way, self-consistency, it's a more interesting way of self-consistency and majority, which actually improves performance with guarantees, because to the extent the verifiers are correct, in fact, the things that come out are correct. And I would actually argue that LLM-Modulo unifies all the same uses of standard LLMs in reasoning problems. So you can argue with me during the coffee time. So in fact, if you think of alpha proof, alpha geometry, fun search, they all use LLMs as generators, and they use classical verifiers to check that the things are correct. You can't actually provide a proof that looks like a proof and say, hey guys, try it out. That's not considered math. And so if you have a proof, it better be checked. And so it's the verifier that checks it, and the LLMs are generating potential proof strategies. LLMs are generating, so that's basically the important thing. And I think AlphaSolve is a continuation of Unsearch. It again can be seen in terms of LLM-Modulo. Another thing that I want you to think of is if you think of code and you want LLM to produce code that is verified correct, the usual way you verify code to be correct is you have unit tests, and if the code is in Python form, Python interpreter can run the code with the unit test input, check with the output, agrees with the unit test exam. If so, it's a partial verification. That's how you actually improve. Otherwise, most of the time, people essentially eyeball the code and say, it looks good enough for me, and I'll try to take it. But if you want actual guarantees, this is what you do. So think of verification in the inference time as a way you can essentially get this. So the spectrum of ideas for test time scaling, and I focus more on the LLM-Modulo. What I will do in the afternoon is actually push this verification in the inference time into the training time, right? Which is if you know how to generate correct solutions, right? Basically, one of the things that Winsky, I showed you yesterday, basically says is, the whole point of intelligence is to push the test part of generate test into generate part, and you can understand much of what's going on in post-training methods and RL-based or SFT-based methods in terms of that. And once again, when you do that, LLMs become better generators, not necessarily with guarantees, but much better generators. And those are the ones that I basically call the LRMs, and we'll talk more about that. Thank you. No, so basically, the partial verification is still better than no verification.
Yes.
Okay. If you want complete guarantees, then you essentially have a verifier that's always sound and complete. That is, it will say every correct solution to be correct, and if it says the solution is correct, then it is correct. That's sound and complete verifiers. But if you just have sound verifiers, even if they are not complete, that is partial verification. So in the case of programming, that's essentially what you're doing, right? Because you check whether the unit tests have, corrected.
From a vision of alpha proof.